what the title suggests, I talk about amoeba, which is not a concept in biology, but a concept in algebra geometry, and somehow it's derived in string theory. So of course, the audience here do not need any motivations to apply machine learning. Otherwise, we won't be sitting here. But let me just mention some background for the completeness of the story. So we've been using like various computer software in our research, and of course we been making like practice results using the software, and as the theme of this workshop, machine learning has also become a very useful tool. So now for experimental mathematics, so I've just mentioned like we have computer-assisted proof, we have online database, and also like Ulam spiral. So well, the story was like Ulam got bored in a conference, so he started to run down numbers in a special sort of pattern, and he found some like special sort of distributions of the primes. So yeah, and also in string theory and mathematics, well, there is physicists using mirror symmetry and of course computers to predict the number of rational curves for the quintic threefold. And more recently, for a special type of polytopes called reflexive polytopes, there's a conjecture regarding the volumes of the associated Sasaki-Einstein manifolds, which is expected to be bounded by certain topological quantities in this paper. And of course, machine learning is also a tool in experimental mathematics. So yeah, you just saw this picture, and so in Strings 2024, people collected 100 open questions in the field, and here are two of them. So Yuji Tachikawa raised this question, and I also saw people asking online about this hint, about this large language model. So he's asking whether Yuji is really joking about this, given his special sense of humor. So I've never asked Yuji, but we all know that nowadays the large language models have really impressed us in our daily life and maybe even in research. Also, Masahito Yamadaki raised this question about reinforcement learning. So of course, this is not a really new idea. I mean, I first learned about this when Fabi Ruler talked about reinforcement learning in string landscape, and also we have some talks applying reinforcement learning in this conference. So, and of course, I'm not able to answer these questions today. I'll just mention one almost trivial application of machine learning to the concept of amoeba, but I hope it will be enough to sort of convey the idea that it's something we can apply to find like more non-trivial discoveries. So basically, we're gonna find some analytic results regarding certain properties of the amoeba. Of course, it's some non-results. At least we can actually derive it on the paper, but still we can see that from these ML results, we can sort of recover these results. So first, I'll introduce some background about the amoeba and its some relevant concepts such as quivers and dimers, and then I'll just discuss the machine learning of the so-called genus of the amoeba. So so I'll spend much of the time talking about the background. So if you know about the quivers, dimers, so you might find it boring. So if you don't know about this background, well, you may also find it boring. So it's a good chance for you to find your own Ulam spiral. But anyhow, we need to introduce the amoeba. So we start with a Laurent polynomial like this with R variables, and this P of Z gives a hypersurface, and we can write the complex coordinates as this X as I plus I theta I, and the amoeba is just the image under the projection of this map. So we just project it to the S coordinates. Of course, we can write it as log Z. And we're going to focus on two variables today. And this image illustrates why this is called an amoeba. So here, this is the the Laurent polynomial. And if we just plot the log Z, and the point set would form a shape like this, and then mathematicians say, okay, this looks like an amoeba, so let's just call it an amoeba. What about the other projection, namely to the like thetas? This is called the co-amoeba by mathematicians and alga by physicists. So in the same example, the projection looks like this. Why do we mention this in physics, especially string theory? So for each monomial like this, we first associate. Yeah. Oh, so this is like the because theta is periodic, so this is just like say the principal value of theta, because it's an angle, so it can be periodic and repeated. So right one is like I just repeat the like thetas. Yeah. Right. So to see the connection to physics, we just first assign each monomial a point n1, n2, where n1 and n2 are the powers of the two variables, and these lattice points would give a the convex hull of the lattice points would give a polygon, which is also called a Newton polygon, like this. And so here we have 5 monomials, so we have these 5 points. And to see it in a more pictorial way, we just show the dual web, the dual graph of the lattice polygon, which is called the web diagram. And then we thicken the graph, the dual graph. What we have is a punctured Riemann surface. So in this picture, if we just project it to a plane, we see that this is the amoeba. I mean, well, roughly speaking, we have some fibrine system to describe the physical theory that will be mentioned shortly, and these fibrines would NS fibrines would just wrap the Riemann surface. For more details, I mean, this sort of amoeba story and connection to like gauge theories was first discovered in the mirror geometry picture in this paper. So I'm just showing the title of that paper, which is called Diamond Models from Mirror Symmetry and Equivalent Amoebae. So you can see how creative people can be when naming things regarding amoeba. But a nice summary can be found in section 5.5 in that paper, where the authors discuss the connections of these different concepts. And conversely, we can take the amoeba, and then it has these tentacles, well, like these 4 legs. They extend exponentially to infinity, asymptoting to some straight lines. And these straight lines are called spines, and the spines are exactly the web diagram we just saw. Oh, from here to here? Oh, no, it's just an illustration. Like if we project it, we have this yeah. Right. So this is the physical theory for our running example. So we have this lattice polygon. These P's and S they are not important right now. But, yeah, but we'll briefly mention the relevant concepts later. So this is from a lattice polygon, and there is an algorithm to construct the physical theory, which is also encoded by this bipartite graph called the dimer, or the brain tiling in physics parlance. So this bipartite graph is on the torus. So this green box shows the sort of fundamental region, namely how it's drawn on a torus. Because it's on a torus, it's periodic, so we can just do the tiling and make it like infinitely large like this. And the dual graph of this dimer or brane tiling gives another diagram called the quiver diagram, which encodes the physical information of the gauge theories, where the nodes are the gauge groups, and the arrows connecting these nodes shows how the matters transform under different gauge groups. And of course, given a Newton polygon and its Laurent polynomial, the dimer model and the quiver is generically not unique. So you can have like different other sort of phases of the dimers following certain algorithms, and these different quivers and dimers are expected to be dual to each other, which is the so-called Seiberg duality. So mathematically, the dimer model is the study of random perfect matchings. And by perfect matching, we mean a collection of edges such that each vertex is incident to exactly one edge. Okay, I guess I can draw one. Okay, sorry about the audience online, but I mean, this should be also straightforward from the definition. But well, just like the example we've just seen, I mean, this is like one box, and one possible perfect matching would just be like this line here and this line here. So this is a collection of edges which contains which connects all the vertices, and each vertex is only incident to precisely one edge. And of course, we're going to choose the two vertical lines, so we have like two different perfect matchings here. And we can actually define something called the height function. So the rough idea is to choose some reference perfect matching like this one, and then we choose a different perfect matching. So we substitute some of the edges in this collection and replace them with a different set such that the new collection is still a perfect matching, like, well, in this case, it's just this one. And the height function is defined in a way such that if I start from infinity, I say, okay, I have height 0. Then every time I go across a closed loop or closed face enclosed by these edges in the two perfect matchings, I increase the height by 1. So if I have a infinitely large graph, then I can define this height function, and here this is an illustration of the example we've just been talking about, and this is like in the limit shape. So if I just choose go to really, I mean, here we're just focusing on one box, but if we really zoom out and choose these random perfect matchings in the sort of, if you like, you can think of this as some thermodynamic limit. We have this amoeba. So the limit in this limit, the height function can actually be described by this Rak-Kyeong function, which is given in turn by the Laurent polynomial as this integral. So this is an illustration of the Rak-Kyeong function, where this gray part it's sort of like a curly surface, and in this paper they refer to this the gray part as the liquid phase, and there is a it looks like circle here. They call it the gas phase, and the other parts are called solid phase. Although it's a smooth function, but it will have like these different phases, and it's the projection on the plane of this Rak-Kyeong function is the amoeba. So
this is also some kind of Merkin model.
Yeah, exactly. So I'm not using that word, but exactly it's the
described by some. kind of polyploid.
I'm not sure about that actually, but yeah, there's some sort of combinatorial model in this context, which we call crystal melting or melting model. But and in this like thermodynamic limit, it's given by this. Oh yes, yes, x, y's are real numbers. Yeah, right. So in okay, I like to interpret it this way. So if you have a say a corner of well, a corner of like boxes, and then you start to remove these boxes, then you would have some sort of shape you get after from removing like a few boxes. But then if you remove like enough boxes, in the end, what you have is a sort of limit shape which looks smooth, and that's what we call the thermodynamic. Yeah. This one. So you choose some reference perfect matching, and then you can like choose different perfect matchings, and then you overlap them. What you have is something like this. If you really, because here it's just like part of the infinitely large picture, but if you really zoom out and this these random perfect matchings, they would form sort of like this closed faces, this shape in the continuous or smooth limit will look like this amoeba. Yeah, okay, I can show a better picture later. I mean, yeah. So yeah, because I was trying. Yeah, okay. Anyhow, so yeah, so this ranking function also arises okay as in this thermodynamic limit, where in this paper the authors refer to them as some sort of emergent Calabi-Yau, and so the motivation is actually more difficult for the machine learning problem. But so here we're just going to talk about a very simple task. But anyway, let me just mention some motivations. So not computing the ranking functions, not computing the actual boundaries of the amoeba is an easy task. So very few analytic results are known. So in our running example, which is like the square, we only know the ranking function for this specific set of coefficients, namely 1 minus 4, which was computed by Subham Roy. So he spent, well, not whole period of PhD, but like most of the time of his PhD, right, computing this ranking function. So if you just compute like well, one ranking function for a certain polynomial, then you can just write a paper. So it's just yes, it's the same thing. So it's just yeah, it's just a name. Yeah. But, right. So but there is something we can some sort of properties we can just see from plotting them. So this the left one is for this -4 coefficient, the right one is for this -5 coefficient, and the most obvious thing perhaps would be the hole here. So if we change the coefficients, the number of the holes, namely the number of bounded connected complementary regions, would change. So here we're just going to consider this simpler problem, namely counting the genus, which is the number of the holes. So so now the inputs would be well, of course, the coefficients from the polynomial, and the output will be the genus. So our question is whether the machine can tell us the right genus, and also can we find any clues if we want to really get some expressions to determine the genus. Well, here this is some observation in Yang Huihe's paper, saying like, well, basically saying something like this, which is sort of like the robustness of the data tends to give similar results independent of the detailed architecture of the algorithm. Well, at least in the problem we're considering right now, this is the case. So I'm not going to show like the detailed architecture of the algorithm, like how actually we don't need to really fine tune the hyperparameters. I mean, we just write down something, just some algorithm, and without any fine tuning, we can get a pretty good result. So in this sense, also it's a relatively simple task. So what we're going to use is something called MDS manifold projection. So here's a one-sentence summary, which says it's basically a projection, namely a low-dimensional representation of the data to more or less to preserve the distances in the high dimensions. Well, this is like copied from the scikit-learn page, so you can always find the detailed explanations from textbooks or the scikit-learn page. So here, this is the example we have, and then we have this projection to. So here we have like an input as a 5-dimensional vector, and these are the 2D projections. As we can see, at least we have some sort of the boundaries of the blue and green points, namely of genus 0 and genus 1. They are sort of separated by 2 straight lines as a cross. So we like to understand like what did the machine do? Like what does it project to? So here are the 2 coordinates. One is for the x coordinates and one is for the y coordinates. So for x, it's relatively simple. Yeah. Oh yeah, so just basically this line. Somehow it's tilted, I'm not sure, but it's this line. Oh, that's what I'm gonna try to discuss. Yeah. Yeah. So right. So for x, it's actually relatively easy to find. I mean, you just fit the points, and you find in terms of the coefficients, and you find it's basically given by C5, the constant coefficient. So here it's the red line is x equal to C5, and then you plot these axis, and then you find that it distributes along this line. And for y, it's a bit subtle, and actually I cheated a little bit here. So this is actually some results we can get once you know something more about the backgrounds, which I will mention later. But roughly, it will get some sort of expression like this. So of course, I mean, you try to fit it with some linear expression will look. Oh, x and y are the projections of the 2 coordinates. Oh, you mean how are they found? Oh no, I'll just do a fit, like linear fit, and then this is basically C5, and that's when it's a bit subtle. Like it's actually something. Well, in hindsight, you can see why it looks like this, but originally it's just some linear combinations of these coefficients. But after you know some analytic background, you can sort of conclude that it should be something like this. But afterwards, it's an approximation. So here I'm just Oh, you mean what does x and y tell us? Oh, it's the next or the next slides. Yeah. So yeah. So yeah. Okay, so the next slide. Yeah. So what actually it says that okay, this is basically the graph we just saw with the blue and green regions. So basically it says C5 is x and this part is 2y. So actually it's just given by this inequality. And well, the red lines are just showing that well you are. I mean, because it's after all, it's just machine I'm not telling machine anything, so it's just doing this simple projection. So there could be some errors in this region. Basically, some say blue points are leaking to the green region and vice versa. But overall, what we have, or what actually this projection says, is that we have this condition to determine the genus. But this is not quite the genus of the amoeba. This is something called the lopsided amoeba, and actually, this is, I mean, I was saying that this part is not actually that obvious. I mean, unless you are student enough, but I mean, usually it's just some linear approximations, and if you really want to say that, okay, I can sense that there is something like this, and I just do the plot against y, it has a nice distribution along this line. I mean, actually, at least for me, I can only do this after I know about this lopsided amoeba. So I would say this is only just sort of recovering the null results rather than giving sort of like results, new results from scratch. Oh, yeah, it's the lopsided amoeba. So as well as I will explain. So what's a lopsided amoeba? Well, I mean, so here I'm just showing one example, but of course we can try different examples. But here it's just an illustration. So we know what an amoeba is. So now we just need to know what lopsidedness means. Well, I mean, just we've been talking about the genus is not easy to write down in general, but we do know that the maximal genus is given by the number of internal points. So in this square example, that's why we only have g equal to 0 or g equal to 1, because there is only one internal point. And also there is a sort of related problem, namely the membership problem. So given the points on the plane, we like to know whether it is sort of a membership of the amoeba, namely whether it belongs to the amoeba. So to study this problem, people have come up with a method using some sort of approximation. So we first approximate the amoeba, and then we take certain limit such that in this limit, the approximated amoeba would recover the actual amoeba, and the approximated one is called the lopsided amoeba. Yeah, okay, so we need to explain what lopsided is. So we say a list of positive numbers is lopsided if one of the numbers is greater than the sum of all the others. I mean, this one is obviously lopsided. And here, the list we would like to consider is this one. Namely, here these MIs are the monomials of the Laurent polynomials, and we just consider this list. So the lopsided amoeba is defined as the set of points such that this list P is not lopsided. So a proposition is that the lopsided amoeba contains the amoeba. So at least we have a relatively crude approximation of the amoeba. Yeah, so it's a real vector. Yeah. It's just a shorthand notation. Sorry, which one? Oh, M1 is the monomial. So because it's like Z1, Z2. Yes. So because I mean here it's a vector, but we put in the monomial, so it's like Z1, then it's just, well, Z1, if it's Z1, Z2, then it's you start from a vector Z1 comma Z2, and you get a monomial Z1 times Z2. So that's basically this M. So oh no, here this is complex, but here this is real list. I'm just using the same letter P. Oh yeah, this is real number. This is real number. Always real number.
And one log inverse is vector, right?
No, log inverse is a vector. M1 is
Then is number, right?
yes, right.
And then still the multiplication or what is the multiplication, right?
Yeah, you mean what multiplication?
K number, right?
Yes. So it's a list of K numbers. Yeah. Then we say it's so like this one here, we say it's lopsided because this one's larger than the sum of the others.
But PG is complex number, PX is the.
Oh, you're right. I'm just using the same letter, but yeah. But this one's real. Yeah, it's actually positive number. It's list of positive. So, right. So we know the lopsided amoeba is the largest set that contains the amoeba, and this is the first step of this approximation. We can. The idea is to find this p tilde n such that when we increase n, it will get closer and closer to the actual amoeba. And this is actually given by this expression for Pn. I mean, if you like, it's called the cyclic resultant, but I mean, that is just this expression. And let's just say Pn is the n-lopsided amoeba. Again, we have this n-lopsided amoeba containing the original amoeba, and this approximation can be made more precise with this theorem. Well, basically, it says that, I mean, for this Newton, I mean, here we're just considering Z2, namely R equal to 2, but in general, you have this coordinates for the Newton polytopes, and they would in turn give some constants, which we call Ci, and we take the max of Ci, and for this constant C, if there is a point living outside the actual amoeba, then the distance, and with its distance is at least some positive number epsilon, then we can always find some sufficiently large n's by this inequality such that this list for Pn is lopsided. So in other words, when we have some points which is not in the amoeba, in the actual amoeba, then we can try to start some approximation with starting from P1, and then if we keep increasing n, eventually we are gonna kick this point outside this approximated amoeba, and hence kicking it outside the actual amoeba, and so that's why it's sort of the reason why it's called the lopsided amoeba. And when n goes to infinity, it converges uniformly to the actual amoeba. So this is an illustration of the lopsided amoeba. So it's a different example. Well, first I'm just being lazy bones, so I'm just copying this figure from this paper. And another reason is that this is a very sort of good example when even at n equal to 8, the lopsided amoeba is not a good approximation, well, at least for genus counting, because you can see it's still very crude because it contains like not only the yellow blue points, but also not only the red and blue points, but also the yellow points. Oh, so P is given by this sort of complicated expression, but it's and then in this way you can do this approximation by computing the following definition of lopsided amoeba. But at n equal to 16, it's already a very good approximation. I mean, there's only like very few points are like living outside the actual amoeba. Right. So for our example we've just talked about, actually everything looks the same. Like 1, 2, 3, 4. I mean, everything looks the same. So for this condition we just saw, this actually gives the lopsidedness, the genus of P tilde 1, namely, the first lopsided amoeba. I mean, you can actually get this also by analyzing the lopsidedness and complementary bounded region for this LA. The reason that we cannot really, I mean, get a sort of more precise condition for the actual amoeba is because at n equal to 1, it's already a very good approximation. So at least I cannot think of a set of coefficients such that the genus will change. I mean, of course there would be, but there will be very, very rare that the genus will be different. So actually, if we look at the previous this example, if you try this 8 and maybe 16, then of course the condition and the projections will look different. But here I'm just showing you a like very, very simple example, and this is actually what we can get from the projections. So I have about 8 minutes. So I'm going to talk about something more random and general. So of course we can consider like, say, what about the alga? And actually it's already studied by Rak in this paper. So you should ask him about what's being done in that paper. And of course, the sort of in this context, the goal is to find, say, the boundaries and of the amoeba and compute the ranking functions, and they are more difficult. So far, I don't have any well clues to how to do this, but still, I hope we can do the computations. And also regarding the quivers, which encode the physical theories we really care about. I mean, of course, we have subduality, and it's something also called mutations in mathematics. And then this concept of mutations not only arise in well gauge theories, but also scattering amplitudes. Although I don't know what scattering amplitude people are doing, but somehow they also have this mutation concept. And there are actually quite a few papers nowadays on machine learning these mutations. There's one example, maybe I think it's worth mentioning. That's when in this paper they have a theorem showing that for when a quiver with 4 nodes is mutation acyclic, namely this quiver is mutation or equivalent to a quiver with node-oriented cycles. And this is actually, well, this is done by machines, but not using machine learning. Rather, it's just by exhausting all the possible cases after reducing to the representative quivers, just like sort of like the proof for color theorem. And now what we are trying to do is to find to use reinforcement learning to see if we can find any sort of invariance of the quivers that is invariant under the mutations. And of course, if we find the invariance, it does not necessarily mean that these invariants will be different and for different mutation classes. So maybe we need to find a set of invariants that would actually distinguish different mutation classes. So so right now, I mean, well, at least like for quiver with 3 nodes, it's relatively easy. You don't need, you just find some, you just have a very robust reward, like saying the distance of two matrices are given by sort of the 2 norm of the, well, I mean, the distance of the 2 quivers are given by the 2 norms of their adjacency matrices, and then you can start from a quiver and you want to get to some quiver after mutations, then it's the machine's going to do a very good job. But for quivers with more nodes, it's more difficult. So there's something we're working on right now. And of course, for cluster algebras, the quivers with a self loop and like 2 cycles, they're not really included in the canonical definition. I mean, there are some mathematics papers discussing this, but still, I mean, we don't have a sort of canonical definition. But in physics, they are really important, and they are related to some superpotential. So another problem is to incorporate this superpotential in the machine learning algorithm.
What kind of cluster?
Oh, you mean for this one?
Yeah.
I don't know. I mean, at least I think we should still satisfy the Laurent property if we have some sort of cluster algebra. But we tried a little bit, but it's not easy to. I mean, we can have some sort of answers or conjecture for the cluster variables, but and the mutation rows, but it's not easy to prove that it's Laurent. So that's the difficult part. Yeah. Anyhow, going back to the 2. Okay, yeah. Going back to the 2 questions. So in the end, maybe I got to talk about something general. So you might think, okay, this guy's talking some big picture. So I mean, using machines, we have different ways to help our research, like machine learning, to generate examples, find new patterns from conjectures, and also we have this LLM to suggest strategies and even do simple proofs. And also we have these formal proof assistants like Lean, which can help us verify proofs, etc. So every time I talk about machine learning, I would like to mention this game called Witness. I'm not sure if you've played this, but it's kind of like the player just sort of woke up in some wonderland, and you are not given any instructions. There are no rules given. You cannot find any like words or and sort of instructions in the game. Then you just explore by yourself, and you find some panel. It looks like a puzzle, and then you try to play with the panel, and you solve the puzzle, and then this puzzle will after you solve it, it will trigger something, or it will lead you to a new area, whatever. So it's kind of like what we're trying to let them machine do. It's just like we throw them with some data, and it's just trying to explore by itself. So in this sense, it's kind of like the machine is like the witness of our research. And so if there's only one takeaway from this talk, so I think it would be like you should play this game. So yeah, that's all. Thank you.